Hello, Mr. Manley here. Today I'm going to be looking at vector dot products and projection. So first of all, let's work our way into the dot product by looking at a problem that we'd like to solve. We would like to find the angle between 2 points. I'm going to say vector u, which is -2, 3. Did I say find the angle between 2 points? I meant find the angle between two vectors. Vector u, which is -2, 3, and vector v, which is vector 1, let's say 1 and -6. Now let's look at the picture of these two vectors. Okay, I've got vector -2, 3, which should be up here. That's this vector. Then I've got vector 1, -6, which is down here. And I want to know the angle between these two vectors. So it's this angle right in here. I want to know that angle theta. Now we could do some trigonometry here pretty easily, right? We could look at this triangle and use some trigonometry to find this angle in here. We could look at this other triangle down here, and then we also already know that that's 90 degrees. So we could piece it together, right? Well, vectors, a vector application is going to allow us to find this with a formula. And the formula that I've got is that cosine of theta is equal to u dot v, and you just heard me say dot, right? So this notation here, that's dot, D-O-T, as in the title of the lesson, vector dot products. So cosine theta is equal to u dot v over the magnitude of u times, not dot now, that's multiplication, times the magnitude of u times the magnitude of v. And then it's simply plugging in some values here. Now, first of all, this dot notation, this dot business here, we're looking for a dot product. And I think the best way to get the dot product instead of drawing it out into a formula is to just show the calculation. The dot product is a calculation that uses two vectors, and for the two vectors that I have, the dot product is -2 times 1 plus 3 times -6. So look at those numbers and see if you can understand how the dot product is calculated. Okay, then I'm also going to do the magnitudes, and I'm going to do these kind of pretty quickly in my head. The magnitude of u is rad 13. The magnitude of v looks like rad 37. And then to get theta, I'm going to do the inverse cosine of all this, right? And I'm not going to take a step and write that all out. But if I want to solve for theta, I'm going to do the inverse cosine of both sides. So I'm going to want to do the inverse cosine of all of this in order to find theta. And like I said, I'm not going to write that all out. And with a little calculator key in, I'm going to get 155.8 degrees. Always nice to draw so that I can look and say, yes, that does look like it could be 155.8 degrees. And the main idea here, of course, is that I've used this formula to introduce you to the dot product. So that is the dot product of u and v. I'll just look at one more dot product out of context. just for an example, if I had vector v is equal to 5, negative 4, and vector u is equal to negative 6, 3, the dot product v dot u would be equal to 5 times negative 6 plus negative 4 times 3. That would be negative 30, negative 42 would be the dot product. Okay? So that's a dot product. It's going to come up in another application that I want to look at in this section, which is called a projection. I'm going to start off by showing you visually what is a projection. So visually, a projection is that I have one vector here, and say I could have any other vector anywhere else. So I could have that vector, some other vector, and say this is vector u, and this is vector v. The way that this is worded, and I'll also simultaneously show the notation, is that we say we might want to find the projection of u onto v. That's how you read this. You're going to find the projection of u onto v. Now, what it means is that if I were to say I was going to put these vectors in standard position. So I've got an xy axis, and now I'm going to move vector u onto the xy axis in standard position there. I'm going to move, and that's vector u, and then I'm going to move vector v in standard position onto the xy axis there. So there's vector v, Now I want to find the projection of u on to v. I've actually chosen a pretty, probably not the best initial example here. But I'll just use the definition, and then I'll give you another example that maybe is a little better. So a way of defining the projection is that I'm going to drop this vector, I'm going to drop its endpoint onto the other vector at a right angle. So the right angle, dropping this at a right angle, is going to put me dropping down here. And then I'm going to have a point of intersection between the point where I dropped it and the line that I'm dropping it onto. So the line that I'm dropping at a right angle and the line that I'm dropping onto are going to have a point of intersection. That is going to indicate my projection. So there, from here to here, that vector is the projection of u onto v. So when we're finding the projection of u onto v, I'll write it since it got covered up there, look down in the left-hand corner. The projection of u onto v, what we're finding is a vector. The projection of u onto v is a vector. Okay? So let's look at another example with numbers. Okay, so here's the two vectors. I want to graph them. I'm going to have vector 5, 2. Which is here, and that's vector u. I'm going to have vector 3, negative 1 here. That's vector v. And I want to find the projection. There's some funny writing for projection here. The projection there of u onto v. So remember how I defined it before? I said that we're dropping a line, perpendicular line, down to the other vector at a right angle. So I'm dropping down from this point, from u onto v. Right? And the projection, which is a vector, is going to be here. So I want to know what is that vector. We could do some trigonometry and some geometry here in order to find out what that vector is. But we have a formula. And the formula is that the projection of u onto v is equal to u dot v, that's a bad dot, u dot v over the magnitude of v squared times vector v. So I'm going to have a real number value here. So the dot product, that just comes out to be a number, not a vector, just a number. The magnitude is just a number. So a number over a number here, and then I'm going to multiply that by this vector. And a vector times a number is going to be a vector. We call that a scalar multiplication, right? So I am actually not going to show you this whole calculation. I'll just see what it is. Okay, so I'm just jumping ahead to the result because I'm running out of time. I like to keep these videos under 12 minutes all the time. If you'd like to know more about this, and also I'm interested in the vector application where we are using vectors to do a work problem, like from physics. If you're interested in that, I could do another video, and you could ask me to do that. But as I say, I'm running out of time on this one, so that will be it for today.